Hi everyone. Through this class, we are going to study about two-dimensional electron gas. Figure shows the ideal energy band diagram of small and capital N gallium arsenide, aluminum gallium arsenide heterojunction in thermal equilibrium. Here we can see that this aluminum gallium arsenide energy gap is wide compared to that of the gallium arsenide. And the aluminum gallium arsenide can be moderately to heavily doped N-type, and gallium arsenide can be more lightly doped or even intrinsic. To achieve thermal equilibrium, electrons from wide bandgap aluminum gallium arsenide flow into gallium arsenide. The electron flow forms an accumulation layer of electrons in potential well adjacent to the interface. The energy of an electron contained in the potential well is quantized. The phrase two-dimensional electron gas refers to the condition in which the electrons have quantized energy levels in one spatial direction. That is perpendicular to this interface, but they are free to move in other two spatial directions. The ideal energy band diagram of a small and capital P heterojunction in thermal equilibrium is like this. The conduction band edge at aluminum gallium arsenide and gallium arsenide heterojunction is shown in this figure A. The potential function near this interface can be approximated by a triangular potential well. V of x equal to E capital E Z when Z is greater than 0 and V of Z equal to infinity when Z is less than 0. Here the origin Z equal to 0 is this point and Z direction is this direction. Schrödinger wave equation can be solved using this potential function. And within this triangular potential well, energy levels are quantized. So this section, it is enlarged in this figure B. Here we can see the different quantized energy levels. Lower energy level E0, next energy level E1. Upper energy levels are not shown in this one. The qualitative distribution of electrons in the potential well is shown in this figure. A current parallel to the interface will be a function of this electron concentration and of the electron mobility. Since the gallium arsenide can be lightly doped or intrinsic, the two-dimensional electron gas is in a region of low impurity doping. Therefore, impurity scattering effects are minimized. The electron mobility will be much larger than if the electrons were in same region as the ionized donors. The movement of electrons parallel to the interface will be influenced by the Coulomb attraction of the ionized impurities in aluminum gallium arsenide. The effect of these forces can be further reduced by using a graded aluminum gallium arsenide heterojunction. The graded layer is AlX Ga1-X As, in which the mole fraction X varies with the distance. In this case, an intrinsic layer of graded aluminum gallium arsenide can be sandwiched between N-type aluminum gallium arsenide and intrinsic gallium arsenide. Figure shows the conduction band edges across a graded aluminum gallium arsenide heterojunction in thermal equilibrium. The electrons in the potential well are further separated from the ionized impurities so that the electron mobility is increased above that in an abrupt heterojunction. This is wide energy gap of N-type material and this is narrow band gap of P-type material. So this figure shows the ideal energy band diagram of capital N small p heterojunction in thermal equilibrium. Narrow band gap of a particular p-type material is this, and wide band gap of another p-type material is this. So this diagram shows the ideal energy band diagram of a small p capital P heterojunction in thermal equilibrium. Now we discuss the general characteristics of energy band diagram. The same delta EC and delta EV discontinuities exist, although the general shape of the conduction band is different in different types of junctions. To achieve thermal equilibrium, in small and capital N heterojunction, electrons from the wide bandgap material will flow to narrow bandgap material. Due to this, a positive space charge region exists in the wide bandgap material and an accumulation layer of electrons exists at the interface in the narrow bandgap material. Since there are large number of allowed energy states in conduction band, we expect a small space charge with Xn and the built-in potential barrier in narrow bandgap material. To achieve thermal equilibrium in small p capital P heterojunction, holes from the wide bandgap material will flow to narrow bandgap material. This creates an accumulation layer of holes in narrow bandgap material at the face. The experimentally determined values of delta EC and delta EV may differ from the ideal values determined using electron affinity rule. One possible explanation for this difference is that most heterojunctions have interface states. If we assume that the electrostatic potential is continuous through the junction, then the electric flux density will be discontinuous at the heterojunction due to the surface charge trapped in the interface states. The interface states will then change the energy band diagram of the semiconductor heterojunction. Another possible explanation for the deviation of the ideal is that when two materials are brought together to form the heterojunction, the electron orbitals of each material begin to interact with each other, resulting in a transition region of few angstroms at the interface. The energy band gap is then continuous through this transition region and not a characteristic of either material.